Paper 1 2018, question 3, let's do this. So I've had to label this because it's a pretty terrible drawing of a Geiger-Müller tube, GM tube here. We've got Pedro holding his tongs. He gets a bit stressed with radiation. He's sweating a bit. He doesn't really need to worry. These rocks aren't that radioactive. At least I hope not. Right, what we need to do is describe how Pedro should use a Geiger-Müller tube to compare the count rates of 2 different radioactive rocks. Now, this is going to be one of those questions where there's going to be a whole list of possible things that we could say. And questions on carrying out practicals are ones that generally students find really challenging. The more you practice, though, the more you think is you've just got to say what you would do. Think step by step, how would this work? How did I do this when I carried out this experiment for you? So if we're going to test the count rates of 2 different rocks, quite simply to start with, we literally just have to put one rock in front of the GM tube. That's it. That's going to be mark number 1. We're going to put a rock in front of the GM tube. And then we are going to measure the count rate Now you've got to start thinking, how are we going to compare these 2 rocks? What do we need to keep the same to make sure any difference we get is about the rocks? So we're going to measure the count rate for a specific time. You could say a time and they'll give you the mark. I'm just going to say for a specific time. There's mark 2. In this case, we need to compare these 2. So I know I mentioned before that if you're asked to change a method or improve a method, you're not going to get marks for repeat. But in this case, the question is comparing these 2. So we are going to repeat this, with the other rock. I could be perfectly sure I'm going to get that mark, keep them separate so that one rock isn't interfering with the count of the other. And there's a mark. Okay, what else could we keep about the same? We need to measure them for the same amount of time, but we also need to keep the distance the same. So keep distance between rock and GM tube the same. And there we go. We would have 4 marks there. Just one other point that we could make that's always worth remembering with these things is we could measure the background radiation and take that away. So measure background radiation. For set time. And there's another possible mark, but we can't get more than 4. So that's what you're going to do. Just think step by step. What do I have to do? Be specific about what things you keep the same, and then any other knowledge like background radiation would be useful to bring in there. Okay, the next one, we're told that a hospital uses a radioactive isotope with a half-life of 6 hours. So half-life is quite a tricky concept to get your heads around. Go through it again if you need it another time, but briefly, it is the time it takes for half the atoms in a sample to decay, or for the count rate to reduce by half. Okay, and we're told that the count rate starts at 80 counts per minute. It might be in becquerels, which is counts per second, but in this case we're told counts per minute, so that's fine. We go with that. It's not going to change what the graph looks like. So we have to complete the graph as accurately as possible to show how the count rate from the isotope will change from the first measurement. So this is a test on, do you understand what half-life means? So we've got to be thinking after 6 hours. Okay, so after 6 hours, or at 0 hours, we have a count of 80. Oh, I can't spell. Apologies, right? And time. So we've got time in hours, and we've got count. So it starts at 80. 6 hours later is a half-life. So that means the count rate will drop by 40, by half. Okay, another 6 hours later, so 12 hours from the original, it's going to half again. It's not going to drop by 40 again, it's going to half. And then one more, 18 hours later, and it's going to drop by half again, down to 10. So the key is you need to plot those points as accurately as possible onto the graph. Plot all those 3 points correctly and you're going to get all 3 marks. I'm going to try and do it here to show you what it will look like. Obviously, you need to be a bit more accurate because you've got more lines on your graph. But essentially, not 20, 18. So you plot those 3 points. If you get any error in those points, there is also marks. I'm going to show you what I want you to do when you're drawing a half-life graph. I'm left-handed. You need to think about what hand you use, but what you want to do is be able to move your wrist so you do a smooth line. So for me, that means turning the page like this, and I can then do a smooth line between those points. Okay, I'll turn it back over. Yeah, so don't be afraid to move your paper around. All right, you can do that if that helps you draw a smooth curve. And remember, a half-life graph, we're never going to touch the x-axis with a half-life graph. Okay, so keep that in mind. That's an important factor. And there we go. That is part B, and we've got all 3 marks if we plotted those points, and then we're going to put our line in as well. And then last part of this, I get this in. Yeah, I think I can get this in at the bottom here. So one radioactive source used in hospital is technetium. It is produced from the radioactive decay of molybdenum, MO. If I pronounce that right, not a chemist here. So it has an atomic mass of 99, atomic number of 42, and what we're told is we're going to get technetium, and we're going to get a type of radioactive decay. Are we told what type of radioactive? So the following nuclear equation. So hopefully you're going to recognize this symbol as beta decay. You're going to recognize this means that it's beta minus decay. Now, the reason that that's happened is something has changed in the nucleus here of our MO. Now, what has changed? I don't want you to try and remember what changes when you get beta minus decay. What I want you to try and remember is that charge has to be conserved. So whatever it is on this side, in fact, let's say plus 42 because we've got 42 protons. It has to also be plus 42 on the other side, and we know this is minus 1. So what do we need? How are we going to get 42 if we're going to have to take 1 away from that number? Well, hopefully you can see that this needs to be plus 43 minus 1, and therefore that would give us our plus 42, so the charge would stay the same on both sides. So if that's going to be plus 43, what's happened? Well, in fact, for this mark, we don't need to know what's happened. We just need to put the 43, but I want you to understand what's happened. So if I'm going to get an extra proton, where has that come from? Well, a neutron has turned into a proton. But if a neutron's turned into a proton, okay, then we still have the same atomic mass. A neutron that did exist is now a proton, so it hasn't changed the mass. That is still going to be 99. It's the proton number that's changed. We know it's a proton that we've gained because that keeps charge conserved. The beta plus decay would be going the other way around, and we'd work that out because we'd make sure that charge in that case stayed the same, but that's not what's happened here. We've got this one here, and there's your mark. And that is the end of question 3. Hope that was useful. If you keep watching, keep liking, I'll keep making these videos to help you with your mocks and exams. See you next time.